Single-phase power involves the transmission of a single alternating current AC waveform through two conductors. These are the live wire and the neutral wire. The live wire carries the current from the source, oscillating between positive and negative values. The neutral wire provides a return path for the current, completing the circuit. The voltage measured between the live and neutral wires is the phase voltage. Now consider three-phase power. In this system, three AC waveforms are transmitted through three live wires and a neutral wire. These three waveforms are offset from each other by 120 degrees, establishing a balanced system. Each live wire carries a different phase of the AC waveform. The neutral wire acts as a common return path for the three phases. The voltage between each live wire and the neutral wire is referred to as the phase voltage. The voltage between any two live wires is the line voltage, which is approximately 1.732 times the phase voltage, specifically the square root of 3 times the phase voltage. Single-phase power finds its use in residential and small commercial settings where power demands are relatively low. Three-phase power is generally employed in industrial and larger commercial applications that require higher power levels. Three-phase power offers several advantages over single-phase power. Firstly, it provides a higher power capacity. Secondly, it ensures more efficient use of conductors. Thirdly, it reduces voltage drop over longer distances. Fourthly, it improves reliability and stability. Recommended reading material includes Electric Machinery and Transformers by Bagas Kuru and Hüseyin R. Hizaroglu, Principles of Power Systems by V. K. Mehta and Rohit Mehta, Electrical Power Systems Analysis and Design by A. J. Wood and B. F. Wallenberg, The Analysis and Design of Electrical Power Systems by Clayton W. Taylor, and Understanding Power System Transients by Clark W. Jellings. Useful websites include Fundamentals of Electrical Power Systems from the University of Texas at Austin, Power Systems Engineering from the Massachusetts Institute of Technology, Single-Phase and Three-Phase Power Systems on Tutorials Point, Electrical Power Systems Explained from Power System University, and Electrical Calculations from Practical Machinist. Understanding how power flows through conductors is essential in electrical engineering. Let's delve into the movement of electrons and the concepts behind single and three-phase power systems. Electricity flows through conductors due to the movement of electrons. In a conductor, such as a copper wire, electrons are loosely bound to the atoms and can move relatively freely. When a voltage is applied across the conductor, an electric field is created, which exerts a force on the electrons, causing them to drift in a specific direction. This directional movement of electrons constitutes electric current. The flow of electricity is often described using conventional current, which is defined as the flow of positive charge. However, in reality, it is the negatively charged electrons that are moving. The direction of conventional current is opposite to the direction of electron flow. In a circuit, electrons leave the negative terminal of a power source, flow through the circuit components, and return to the positive terminal. The components in the circuit resist the flow of electrons to varying degrees. This resistance is measured in ohms. Ohm's law states that the current through a conductor is directly proportional to the voltage across it and inversely proportional to its resistance. Mathematically, this is expressed as voltage equals current times resistance. Single-phase power is the most common type of electrical power used in residential and light commercial applications. It consists of a single alternating current AC voltage source that supplies power to a load through two wires, typically a hot wire and a neutral wire. The voltage of a single-phase power supply varies sinusoidally with time. In North America, the standard voltage is typically 120 volts or 240 volts at a frequency of 60 Hz. The hot wire carries the alternating voltage, while the neutral wire provides a return path for the current. The instantaneous power delivered to the load varies with time, but the average power is constant. Single-phase power is suitable for powering small appliances, lighting, and other low-power devices. However, it is not as efficient as three-phase power for high-power applications. Three-phase power is widely used in industrial and commercial applications where high power levels are required. It consists of three AC voltage sources that are 120 electrical degrees apart in phase. These three voltage sources are typically connected in either a Y, also known as a star, or a delta configuration. In a Y connection, each voltage source is connected between a phase terminal and a common neutral point. The voltage between each phase terminal and the neutral point is called the phase voltage. The voltage between any two phase terminals is called the line voltage. The line voltage is equal to the square root of 3 times the phase voltage. In a delta connection, each voltage source is connected between two phase terminals, forming a closed loop. The voltage between any two phase terminals is the line voltage, which is equal to the phase voltage. The current flowing through each phase terminal is called the phase current. The current flowing through each line is called the line current. The line current is equal to the square root of 3 times the phase current. Three-phase power offers several advantages over single-phase power. Firstly, it provides a higher power capacity for a given voltage and current. This is because the power delivered by a three-phase system is the square root of 3 times the voltage times the current times the power factor. Secondly, three-phase power is more efficient than single-phase power. This is because the instantaneous power delivered to the load is more constant, resulting in less power loss. Thirdly, three-phase power produces a smoother torque in electric motors, resulting in improved performance and reduced vibration. Fourthly, three-phase power is more reliable than single-phase power. If one phase fails, the other two phases can continue to supply power, although at a reduced level. In commercial buildings, three-phase power is typically used to power large equipment such as HVAC systems, pumps, and elevators. It is also used to power lighting systems, computers, and other office equipment. In residential buildings, single-phase power is typically used to power most appliances and lighting. However, some larger appliances, such as electric stoves and air conditioners, may require 240 volts single-phase power. Understanding the concepts of single-phase and three-phase power is essential for anyone working with electrical systems. These concepts are fundamental to the design, installation, and maintenance of electrical power systems in residential, commercial, and industrial applications. To visualize what's going on in an electrical system, it helps to understand the flow of electrons and the behavior of AC voltage and current. Consider a simple single-phase AC circuit consisting of a voltage source, a resistor, and connecting wires. The voltage source produces a sinusoidal voltage waveform that varies with time. The electrons in the circuit are driven by this voltage flowing from the negative terminal of the source to the positive terminal. As the electrons flow through the resistor, they encounter resistance, which impedes their movement. This resistance causes the electrons to lose some of their energy, which is dissipated as heat. The amount of current flowing through the circuit is determined by the voltage and the resistance according to Ohm's law. The current also varies sinusoidally with time, in phase with the voltage. Now consider a three-phase AC circuit consisting of 3 voltage sources, 3 resistors, and connecting wires. The 3 voltage sources produce 3 sinusoidal voltage waveforms that are 120 degrees apart in phase. The electrons in each phase of the circuit are driven by their respective voltage source. The currents flowing through each phase are also 120 degrees apart in phase. The total power delivered to the load is the sum of the powers delivered by each phase. Because the 3 phases are balanced, the total power is constant, even though the instantaneous power in each phase varies with time. To further visualize the flow of electricity, you can use an oscilloscope to display the voltage and current waveforms. An oscilloscope is an electronic instrument that displays a graph of voltage or current as a function of time. By observing the waveforms, you can see how the voltage and current change over time and how they are related to each other. You can also use a multimeter to measure the voltage and current in a circuit. A multimeter is an electronic instrument that can measure voltage, current, resistance, and other electrical parameters. By using a multimeter, you can verify that the voltage and current values are within the expected range. In addition to understanding the flow of electrons and the behavior of AC voltage and current, it is also important to understand the concepts of impedance, power factor, and harmonics. Impedance is the total opposition to current flow in an AC circuit. It is a combination of resistance and reactance. Reactance is the opposition to current flow due to capacitance or inductance. Power factor is the ratio of real power to apparent power in an AC circuit. Real power is the power that is actually used to do work, while apparent power is the total power supplied to the circuit. Harmonics are sinusoidal voltages or currents that have frequencies that are integer multiples of the fundamental frequency. Harmonics can cause problems in electrical systems, such as overheating of equipment and distortion of voltage waveforms. By understanding these concepts, you can gain a deeper understanding of how electrical systems work and how to troubleshoot problems. Furthermore, it is beneficial to explore resources that use animations and interactive simulations to demonstrate the principles of electricity flow. Many online platforms and educational software packages offer these tools, allowing you to visualize the movement of electrons, the propagation of electromagnetic fields, and the interaction of electrical components in a dynamic and engaging way. These visual aids can greatly enhance your understanding of complex electrical concepts and make the learning process more intuitive. The NEC, or National Electrical Code, provides standards for safe electrical installations. For example, NEC Table 310.15 details ampacities of insulative conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, not more than 3 current carrying conductors in raceway cable, or earth, based on ambient temperature of 30 degrees Celsius. The ampacity is the current in amps that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. These tables are essential for ensuring that conductors are properly sized for the expected current load, preventing overheating and potential fire hazards. For instance, a 12 American wire-gauge copper conductor with a 75 degrees Celsius insulation rating and installed in a raceway with no more than 3 current-carrying conductors has an ampacity of 25 amps according to the NEC. Similarly, a 14 American wire-gauge copper conductor under the same conditions has an ampacity of 20 amps. It is crucial to consult the NEC tables to determine the appropriate ampacity for various conductor types, insulation ratings, and installation conditions to comply with safety regulations and ensure the reliable operation of electrical systems.